Hi viewers, before proceeding to semiconductor, I briefly discuss about other two types of materials, which are conductor and insulator. Conductor is a material that easily conducts electrical current. For example, copper, silver, gold, aluminum, etc. While an insulator is a material that resists the flow of electric current. It does not prevent the flow entirely. For example, rubber, porcelain, glass, wood, etc. The conductor has only one electron in its outermost shell, which is called valence electron. This valence electron very loosely bonds to the atom and can easily break away from its atom to become free electron, which is responsible of flow of electricity. While in an insulator, valence electrons are tightly bound to their atoms and cannot easily break away to become free electrons. As a result, insulators have very few free electrons available for electrical conduction. Now come to main topic, semiconductor. A semiconductor is a material that lies between conductor and insulator in terms of its ability to conduct electricity. A pure semiconductor is neither a good conductor nor a good insulator. It does not completely resist the flow of electric current, nor does it allow current to flow freely like a conductor. Examples of semiconductors include germanium and silicon. Single semiconductor element has 4 valence electrons. Then how conductivity be improved in semiconductor? The conductivity can be drastically enhanced by controlled addition of impurities to pure semiconductor material. This process known as doping. This makes semiconductors ideal for use in electronic devices such as transistors, diodes, and integrated circuits, where precise control over electrical current is necessary. There are 2 types of impurities, N-type and P-type. The N-type semiconductor is formed by adding pentavalent impurity to pure silicon. Pentavalent impurities have 5 electrons on its valence shell, such as phosphorus, arsenic, and antimony, etc. Here is an antimony atom with 5 valence electrons. Each antimony atom forms covalent bond with 4 adjacent silicon atoms, leaving 1 extra electron. This extra electron becomes free or conductive electron because it is not attached to any atom. The number of free electron can be carefully controlled by number of impurity atoms added to silicon. These electrons are also called majority carriers. As this material holds negative charge carriers as majority carriers, thus it is called N-type material. The P-type semiconductor is formed by adding trivalent impurity to pure silicon. Trivalent impurities have 3 electrons on its valence shell, such as boron, indium, and gallium, etc. However, since boron only has 3 valence electrons, it can only form 3 bonds with the silicon atoms. This leaves a deficiency of 1 electron in the bond, which creates a hole. Because holes are the majority carriers, the most abundant charge carriers in this material, P-type material is so named, indicating the presence of positive charge carriers. The minority carriers in P-type material are free electrons, but they are much less abundant than holes. This hole represents the absence of an electron, and it can act as a positive charge carrier. The hole is ready to accept an electron, and when an electric field is applied, the hole appears to move through the lattice as electrons from neighboring bonds jump into the vacancy. This movement of holes constitutes the flow of electric current in the material. The number of holes can be controlled by the concentration of the boron or other trivalent dopants added to the silicon. The more dopant atoms present, the greater the number of holes, thereby increasing the p-type conductivity of the material. Thanks so much for watching, everyone. I hope you found this video helpful. If you did, don't forget to give it a thumbs up and hit that subscribe button so you never miss an update.